last episode, we started to dive into exoplanets, and today we're going to continue that stellar journey into seeing what kind of new science and technology that we're using.
So we've got our good friend Jonti back from the University of Southern Queensland, and we've also got Jonah here today joining us. And Jonah is a PhD candidate at the ANU, a bit of an expert on researching exoplanets, and also up at Mount Stromlo Observatory.
Yep, that's
doing
correct.
research out of there. Thanks for being here.
Yeah, thank you.
Thanks, guys. What's some of the science and technology that we've been using to discover exoplanets?
So, I mean, last episode we talked a little bit about the winking method, or when a planet crosses over a star, sometimes the starlight will dip a little bit, and you can kind of see that there's a planet there as it dips the starlight. And then there's another method, the radial velocity method, where you can kind of see a star wobble a little bit as the planet goes around the star, kind of pulling and pushing on the star as it goes around. And these are what we call indirect methods of detecting exoplanets. And they've been really successful for the past 30 years or so, and most of the 5,000 or so we've detected so far have used these. But they're not really what we want. What we would really like to do is to find light coming off of a planet directly, like take a picture of a planet and take the light from it so that we can then analyze it and see exactly what might be in the planet, what might its atmosphere be like, and that kind of thing. But it turns out taking a picture of a planet is really, really hard for a bunch of reasons. For one thing, stars are really, really bright. So you can kind of imagine it a bit like a firefly next to a car headlight, only much, much worse.
Oh, dear.
We're talking a factor of about 10 billion times brighter.
Just a little bit brighter.
And so what you need to be able to do is to kind of remove that starlight. And one such way to do that is to simply block it out using like an umbrella. So one thing with there's a new telescope coming out called the Nancy Roman Grace Space Telescope. And what is going to be attached to this telescope is something called a star shade, which is a huge, big, you kind of think of it as a bit of a screen that's flying hundreds of thousands of kilometers away from the telescope. You can precisely align it up so it blocks out the starlight, but it's just small enough that it doesn't block the planet going around it. So you can kind of eliminate the starlight, but seeing the planet go around, which is pretty cool.
That is very cool.
When's that due to launch?
Oh, good question. I'm not 100% sure. Jonti, do you know when it's launching?
I think it's looking at the late 2020s or early 2030s.
Yeah, something like that.
So you're doing a lot of work on that photography side of things of exoplanets. Is that
Yeah.
where you're
Kind of. So my main work is actually focusing on a kind of a separate path of trying to take these direct images. Because there's another factor involved, which is planets are really close to their stars. And in order to distinguish between them, you need really, really big telescopes. We're talking 30 to 100 meters big. And turns out you can't really build mirrors that big. We're trying, so we've got a couple really big telescopes coming up called the Extremely Large Telescope for one, or the 30-meter telescope. $100 if you can guess how big that mirror is.
Shame we didn't get OWL, which was the overwhelmingly large telescope.
Oh, that would have been great. But yeah, you need these really big telescopes to kind of distinguish between a planet and the star. And one way you can get around this issue is by, instead of having just one big telescope, you have a couple small telescopes spread apart by about, say, 100 meters or so. And they can kind of work together through some sciencey magic called interferometry.
Piecing the image together.
Yeah, it kind of pieces together and it creates one big telescope that can kind of distinguish between them. And so I work on that technique.
Yeah. And it's something that's been done really successfully in the radio for a long time, but it's a lot harder in the optical, isn't it? Because the wavelengths are shorter, so everything gets harder, essentially.
Yeah, with radio telescopes, like, in fact, Australia pioneered the technique in order to kind of connect these telescopes up and use them to create a bigger telescope that wouldn't have the resolution of a single telescope. But yeah, with optical telescopes, you need to make sure that your telescopes are separated and you know they're positioning to within 1,000th of a millimeter. So incredibly hard, but we're trying, and we've done it successfully with some telescopes over in Chile and the US.
So you obviously quite a challenging field. What are some of the other challenges that you come across when looking for exoplanets?
Well, I mean, I would say those are two of the biggest ones.
Yep.
Just how bright a star is and how close it is to the star. And so overcoming the resolution requirement requires big telescopes. Overcoming the kind of the brightness of a star generally means you have to move into a region where the planet is brighter and the star is fainter. And if you're, say, wanting to look for a terrestrial planet, so a planet a bit maybe like Earth, you have to kind of move into what we call the mid-infrared. So you, like if you've ever seen like a heat camera or something, this kind of region where the planet is a lot brighter than when it is in the visible.
Right.
Where you reduce the difference between the star and the planet to only about 10 million times brighter.
So much better.
And this is why a lot of planet finding telescopes are in space, because there's something else that's about the same brightness as an exoplanet like Earth, and that is the Earth and its atmosphere. It's kind of like a big opaque blanket at these wavelengths, and so got to get above it, send it up into space.
Yeah, there's lots of different problems. Every method that we use to find planets is plagued by problems. And some of them are down to the fact that with the indirect methods, there's lots of other things that can look like a planet. Really good example of star spots. We've had challenges for the radial velocity technique, which is measuring the wobble. Because if you've got a star spot, that's a cooler patch on the star. As it rotates around, it can pretend to be a planet for a couple of orbits before it goes away. If you're using the wink technique, there was a famous case of planets getting killed recently because we thought there was a planet going around a single star, but it turned out in the same pixel, there was a binary star in the background that was much, much fainter, that was eclipsing, that was making a dip in the brightness of that pixel that was just the same as you'd have with a planet around the foreground star. So every method you look at has these challenges, and that's why the technology gets developed. That's why we get so much new cool stuff coming out, because we're pushing the boundaries of what is feasible, of what we can actually do.
That is great to know. What is some of this technology? Obviously, you mentioned the umbrella, as I colloquially call it. We can put satellites into space telescopes into space to help us see. What else can we do? Is there much that we have control over?
Oh, well, one of the technologies that I actually work on a day-to-day basis with this kind of technique where you've got these multiple small telescopes trying to work together into a big one and trying to make sure these telescopes are all the same distance apart, is if you want to put these telescopes in space, you need to make sure the satellites can all move around and be in position to within a thousandth of a millimeter. This kind of formation flying, as we call it, which is something that a lot of companies like SpaceX and Amazon, who are launching these huge mega constellations, all need to keep in mind. We're also helping out with that and trying to keep these satellites exactly the same distance apart.
Do you, I guess it's a pretty popular question in the media at the moment, do you see a place for humanity beyond Earth?
Absolutely. From my point of view, I mean, I don't know, Jonah, what you think of that.
Well, I'm possibly on the more pessimistic side, where I mean, planets are just so far apart, like other stars. So you take, for instance, our closest star, which is Proxima Centauri in the Alpha Centauri system. It's 4 light years away, which is a really, really long distance. It means that if you're traveling as fast as you can at the speed of light, it's still going to take you 4 years to get there.
To put that in perspective, it took us several days to get to the moon, and the moon is 1 light second away. 1 1/3 light second, so Proxima's a long way away.
And like one of the fastest satellites we've ever launched, Voyager, has only just left the solar system, and that was launched in the 70s.
And this is a subject to much debate, and we could go really off topic. So I have a dynamics background. I'm interested in gravity, and to me, the outer edge of the solar system is between 1 and 200,000 times further from the sun than the Earth, because there are comets out there held by the sun that are halfway to the nearest star. So for me, Voyager will not leave the solar system for 10,000 years. For people who study the sun and the solar wind, the sun's blowing a bubble into space, and there's this thing called the heliopause, which is a point where the bubble the sun's blowing impacts the stellar winds from every other star in the galaxy. That's what Voyager's crossed. So it's one of these really interesting things about science, that every scientist you talk to has a different definition for where the solar system ends, because that is relevant for their science. And it's a problem we have with why we define planets the way we do, why we define children, adult, pensioner, all the rest of it. We have something that is infinite in scope and continuous, and we have to put divisions in it. And if you get 3 scientists in a room, you'll get 4 answers as to where the solar system finishes.
Yeah.
That, it's maybe a little bit off topic, but something that has always intrigued me. There's been talk about us finding other planets within our solar system. Do you, Jonah, I'll start with you. Do you think that's possible? Do you think there's other planets that we've just missed?
So I think there's certainly some evidence for another planet, so-called Planet 9, based on looking at some of the outer solar system objects and how they're clumped, and the gravity kind of shows that there might be another planet there. But so far, despite our best efforts, we haven't found it yet.
And one of the explanations is that this planet's there, but one of the challenges is our observations are biased. It's easier to find objects away from the Milky Way than it is to find them where the Milky Way is, because the Milky Way gets in the way. There's lots of stars there. The other explanation for this signal with Planet 9 is simply that we find things where it's easier to look, and we're finding things right at the limit of what we can do. I think there's a very real chance we'll find objects that are planet-sized in the solar system still, but that will challenge our definition of a planet. There will have been objects the size of the Earth formed in that region between Jupiter and Neptune that were ejected into this thing called the Oort cloud, the cloud of comets around the solar system. If you've got something the size of the Earth halfway to the nearest star, is it really a planet?
Yeah, it's a fascinating topic, and it does hold a very important part in all of our lives and what it means to be human. And I guess that's why we all love this side of science, because it's beyond who we are. Thank you so much for joining us again today. It was a pleasure having you all here. Thank you for joining us, and hopefully catch you on the next episode of Stellar Journeys.